Hello everyone, welcome. Let's look at some basic types of signals in this lecture. There are 4 basic types of signals. Now what is this continuous in time and continuous in value signals? Let's look at it. Let's say I take a signal f of t. This signal exists between t is equal to 0 to 8, t is equal to 8. And let's take the positive maximum amplitude as plus 3 volt and the negative maximum amplitude as minus 3 volt. When we talk about continuity in time, in this example, the signal exists between 0 to 8. Now within the 0 to 8, at any time t, if the signal is present, then that signal is continuous in time. For example, this is the t is equal to 2 time. Now at this t is equal to 2, you can see that it is at the maximum. So the signal is present and therefore it is continuous in time. If you take any other thing, let's say if you take 6, you'll find it here. The signal is present. Between 0 to 8, it is present at any time t and therefore the signal is a continuous in time signal. Now let's look at the other term, continuous in value. Now if you look at this plus 3 volt and this minus 3 volt, the signal is fluctuating between the plus 3 volt and minus 3 volt. Now I can confidently tell that for any time t, the signal would have traversed every value between plus 3 volt and minus 3 volt. At different t, there will be different types of values, all within the range of plus 3 volt and minus 3 volt. Like for example, something is here, something is here, something is here. So every value between plus 3 volt and minus 3 volt will be accessed by the signal, and therefore we can tell that this signal is continuous in value. Now for example, between plus 3 and minus 3, if I take 1.5 between plus 3 and minus 3, I can easily tell that the 1.5 volt is here and it is between plus 3 and minus 3. Therefore, the signal is continuous in value. So this is the first basic type of signal, the signal which is continuous in time and continuous in value. Now let's move on to the next type of signals. The next type of signal is the continuous in time but discrete in value signals. Suppose we have a signal x of t with respect to t. In this signal, we can see that there are dotted lines. The dotted lines in this signal denote that the values in the signal are discontinuous. Let's say at this point t is equal to 1 second and at this point t is equal to 2 seconds, and this is obviously 0. So we can see that at t is equal to 1 second, this value is at plus 3 volt, and at the same time at t is equal to 1 second it is also at minus 3 volt. So there is kind of a discontinuity between these values. So from t is equal to 0 second up until t is equal to 2 seconds, we can see that between 0 and 1 second the signal is at plus 3 volt, and between 1 and 2 second the signal is at minus 3 volt. Therefore this signal is a continuous in time signal because at any time t within the time period, the signal exists. At t is equal to 1 second and 2 second, it may exist in different points, but there is a specific value to that signal at that time. But if we talk about the value of the signal, the only value that the signal takes is plus 3 volt and minus 3 volt. We can't see plus 2 volt, 1.2 volt, minus 1.2 volt, anything. So between plus 3 volt and minus 3 volt, no value is taken by the signal. It only takes plus 3 volt and minus 3 volt at different instances of time. Therefore, we can tell that this signal is a discrete valued signal. Overall, this signal is a typical example of a continuous in time but discrete in value signal. The next type of signal which we are going to see is discrete in time but continuous in value signal. Before we talk about this discrete in time signal, I would like to give you a brief introduction to how this discrete in time signal came. First, you have to take a continuous time signal. Let's take the same signal which we took for the first example. If we take another signal like this, and all the points which are between these spikes are 0, then if we multiply both these signals, we are going to get a signal like. So in this signal we can see that wherever the signal is present, the value is only 1, and wherever the signal is not present, it is 0. So if you multiply this signal having 1 at some specific time with the continuous time signal, this value 1 is going to be multiplied with whatever value that x of t is having at that particular point of time, and that is going to be shown in this diagram. If I increase the number of values of 1 present in the signal, then more number of points in the x of t will be shown in the multiplication. Now when we multiply this signal with this, then the signal will look something like this. The points at which the signal is 1 for this signal is going to be multiplied with the continuous time signal, and this 1 is going to be multiplied with whatever value x of t is having, and it is going to be shown in the result. Wherever the signal is 0 in this signal, the product is also going to be 0 and it is not going to be shown. And that is how we end up with a discrete time signal which is represented as x of n. N denotes that it is not a continuous time but it is a discrete time, meaning it takes values 1, 2, 3, 4, something like that. It is not 1, 1.1, 1.05, 1.2, nothing like that. It is 1, 2, 3, 4. It is discretized. The time is discretized and we get n. So I've taken the name of this signal as p of n. It is a discrete signal and it is denoted as p of n. And when we multiply both these signals, I've represented the result as x of n, and it is the product between x of t and p of n. Now let's focus on this result signal x of n. Now we can see that at 0 the signal is defined, at this instant the signal is defined, but between 0 and this instant, let's say this is 1, we can see that there is no signal present. Therefore we can tell that this is not a continuous time signal. It is a discrete time signal, because for continuous time signal at every instant of time the signal should be present, but we can clearly see that between 0 and 1 there is no signal present. So this is a discrete in time signal. But if we take the value of the signal, any value between plus 3 volt and minus 3 volt is possible. For example, there is 1.5 volt, there is 2.3 volt, there is 3 volt, and so on and so forth. So this signal is a continuous in value signal. Now there may be a confusion here, like how is this continuous value? There is 1.5 volt, there is 2.3 volt, where are 1.6 volt, 1.7 volt, where are they? So if you multiply 1.6 volt with 0, you're going to get 0. That is exactly what is happening here. So there is 1.6 volt and there is 1.7 volt. But if you multiply it with 0 here, then you're going to get 0 and you're not going to see any signal at that moment. So there is no value of 1.6 volt. That is why, though we are not able to see the values, it is continuous value. Also, if we take more number of samples in P of n, we will get a more closer diagram, and therefore it is a continuous value signal. Therefore, this is a typical example of a discrete in time but continuous valued signal. The fourth and the last type of signal that we are going to see is the discrete in time and the discrete in value signal. Now if we take a look at the result which we got from the third type of signal, it is a discrete time signal. But the value is not discrete, and now we have to find a way to make the value discrete. Because as I said, there is a lot of values 1.2, 2.4 and so on and so forth. And one more thing, the process of multiplying this continuous time signal x of t with this discrete time signal is called sampling. Sampling is a very important topic and I will discuss it in the coming lectures. So in sampling, you take a continuous time signal and multiply it with an impulse train. The process of doing this is called sampling, and you get a sampled signal. Now coming back to the question, we have got a sampled signal which is discrete in time but continuous in value. Now we want to make that discrete in value also. How do we do that? And for that, you have to do quantization. Simply speaking, quantization means rounding off the values. To better understand quantization, if you have only 0 and 1 value and the value of your signal comes to around 0.5, then quantization says that it should be taken as 0, or anything which is less than 0.5 should be given as 0, but anything greater than 0.5 should be given as 1. So that is how you quantize values of the signals. So with reference to this diagram, we have values 1.5, 2.4, 3 and so on. Taking reference from this graph, we will perform quantization to this. Now the first value is 0. 0 is 0. So you mark 0 here. And the next value is 1.5. Now as per quantization rule, if we are given a value of 1.5, it should be rounded off to 1. So at this point it is 1 volt. The next point is 2.4. Again we are going to round it off to 2. The next point is 3. So we are going to keep it as 3. If the next point is 1.6, right, you have to round it off to 2 again. And if the next point is 0.2, then you have to round it off to 0. So that is how you perform quantization. And now you can see that all the values are discretized. They can't take any value. It can take 1, or it can take 2, or it can take 3, or it can take 2 again, or it can take 0. So the values are getting quantized, and the discrete in time still holds true. Thus we have a quantized signal. And this signal is the example for a discrete in time and discrete in value signal. So these are the 4 basic types of signals. We are going to take different tools and analyze different signals, which are all based upon these 4 types of signals. Another important point is that if a signal has some continuity in it, then it is an analog signal. But if the signal is of discrete time and is of discrete value, then that signal is called digital signal. With this, I would like to conclude the lecture on the basic types of signals. Thank you for joining. See you in the next one.